Let us start our lecture on solid-solid transformation and nucleation rate. It is the lecture number 18, and as we are discussing that how this straining of lattice takes place in order to have a match between the lattices between of parent and product phase. This is my product parent phase and this is my product phase, that when beta is appearing in the solid alpha, both the phases are solid. Now, when this kind of lattice matches are there, for example, in case of copper silicon system, we have seen that the kappa phase and alpha phase both have perfect lattice match along 111 as well as 001 plane for HCP as well as for FCC, and at the same time the angles, this direction for those planes 110 as well as 112/0, they are having a match, they are parallel also. So, that time we have a perfect lattice match, and that time the chemical energy, interfacial energy would be the interfacial energy. But in this case there will be two factors, one is chemical because of the compositional changes as well as the structure effect, and the structure effect is coming due to this lattice straining part, and this lattice strain is leading to the strain energy and which is volumetric in nature. At the same time this has a positive nature. Okay. Now, interestingly, this particular interface as well as in case of copper silicon where we have a perfect match, we call it coherent interface. This is coherent interface. Now, situation would be different. Let us say we are having match like this because of the straining of the lattice, but at some point of time this particular bending will not be allowed if it requires too much of bending. So, that time it will create another situation which is called incoherent interface. So, now these are the matching part, but if further bending is not allowed, then if this is the further bending it requires. So, this much bending if it is not allowed, that time the lattice of the parent phase would not have anything below, rather it will start like this. Okay. So, now this is an extra plane on top of this particular line, and this is looking like this. So, this is a kind of dislocation. So, whenever this extra strain energy which is required for the lattice bending, okay, that is not permitted. So, then that much of energy will be stored in the form of dislocation. So, there will be extra lattice plane on top of this particular interface and there will be no plane below this, and then again the situation will continue. At some point of time there will be another lattice plane like this, which will be again this kind of situation. So, this there will be one other situation like this, there will be another a lattice plane on top of this is another dislocation. So, like that way there will be creation of dislocation along this particular interface in order to take care of that extra lattice distortion. Okay. So, that time it is called incoherent, semi-coherent. Semi-coherent, and that time it will be again part of this particular interface will have two contribution, one is structure, one is chemical, and this structure contribution would lead to the strain energy of the lattice. And similarly there will be one more interface which we call as incoherent interface, and that time there will be no lattice match between the parent and product phase. So, if we have a situation like this, if this is the lattice alpha, if this is the lattice alpha, there will be one other lattice of beta. This is beta, this is alpha, let us say, and this is the interface. That time there will be no match between the lattice planes, and that time it is called incoherent. Now, it is pretty clear that here the energy of the interface would be very high, here it will be in between, and here it will be the lowest, but still there would be existence of strain energy, and these strain energy is coming into picture because here we are considering solid solid transformation. And once we know that, then the procedure is exactly similar what we have followed in case of liquid solid transformation. That time this would be the energy. So, this is again volume term delta Gs, which is positive. Okay. This is also positive. So, now if I try to find out free energy change, total free energy change, it would be minus V. If we do this, delta Gs. So, it would simply like and now if this is spherical, if we consider this is a spherical of radius r, so that time we can calculate what is the critical radius. Critical radius would be 2 gamma alpha beta divided by delta GV minus delta GS. If we do that, that means if we do that equal to 0, you will get to this. Okay. So, once you get this, delta G star also you can calculate, which would be 16 pi 3 gamma alpha beta q delta GV minus delta GS square. Okay. And now this is the expression for activation barrier. And now in this case, activation barrier, now if we compare with the solid liquid case, there were no delta Gs term. So, it was simply gamma liquid SL divided by delta GV, and that time this is solid liquid case and this is solid solid case is, and this one was delta GV square. So, only thing that is the difference is basically delta Gs. Now, we can also calculate delta Gs. For example, in case of coherent interface, we have a simple expression which is delta Gs, which is total, here total equal to 4 mu delta V, delta square V, and here delta is the strain energy and delta is related to A alpha. Okay. So, this A alpha, this is A alpha, this is A beta, and this is the relation, and mu is basically shear modulus, and V is the equal to volume of beta. Okay. So, that means the shear modulus you can get from any material, which is basically the shear strain divided by shear stress divided by shear strain, and this you can also calculate from the lattice parameter, and then you can get the delta Gs term, and you see it is a volume multiplied, that means the volume factor. So, now you can see that this is a simple expression for calculation of strain energy in case of coherency strain. So, you can use that particular formula and to get some idea about R star and delta G star, and once we get that, we can have a kind of graphical representation. If I try to see the graphical representation, I can also have that. Okay. So, the last time what we have done, this is my R and this is my delta G R. So, it varies like this, and that time this is my A gamma alpha beta, and there will be two terms. This will be my delta G V minus delta G S with a negative sign, V negative sign, it is proportional to R Q. But if I try to find out, and these delta G star, which is nothing but this, is decided by this. But if I try to consider delta G V only, that one would vary like this. So, if I consider this one, this entire thing will go to the left. Okay. So, it would appear on the left side. So, this is the kind of energetic situation when we consider strain energy. The strain energy is actually takes the this point towards light, right. Okay. So, if I consider the homogeneous nucleation, that times I do come across this, and if I try to find what would be the homogeneous nucleation rate, would be equal to, it would also have a similar expression, which is minus delta G star plus delta G D by K T, where this delta G star is given here. Okay. And this delta G D is basically, for example, if we have beta in alpha, this alpha atom, when it starts and go to, when it migrates and goes to the beta surface, that time we have to come across another energy barrier, which is delta G D, which is coming from the diffusion factor. Okay. So, that means I homogeneous has got a similar expression what we had in case of I homogeneous for solid liquid transformation. Okay. So, now this is about homogeneous nucleation in case of alpha beta transformation, and that too that is happening at temperature below equilibrium temperature. Okay. And if we know this expression, then we can calculate what is the homogeneous nucleation, which is number of nuclei per unit volume per unit time, and this information will be required in order to construct TTT diagram, because our final aim is to find what is the TTT diagram, which will allow us to go for a different temperature time sequence in order to get different structures in materials. Now, once we know homogeneous one, we can also have a similar expression like in case of heterogeneous nucleation, but in case of heterogeneous nucleation, treatment would be similar, but with a little difference that there it is not, the solid will not form on the mold wall, rather it will form, it can also form on grain boundaries. Okay. So, let us have a look at the homogeneous nucleation part, sorry, heterogeneous nucleation. In case of heterogeneous, solid to solid, that time I can have many things in the materials which can act as a site for heterogeneous nucleation to occur. For example, there could be oxide particles. During solidification, it can entrap inclusions which can be in the form of oxides, which can stay inside the solid. Okay. That can act as a heterogeneous nucleating sites. For example, there could be grain boundaries. In a polycrystalline material where there will be grain boundaries, one grain boundary can act as a heterogeneous nucleating sites. Let us consider that one grain boundary act as a heterogeneous nucleation site, and that time this is alpha, this is alpha in the beginning. In the beginning it was alpha alpha, that means both the phases, this is alpha, this is alpha, this is alpha, and let us say one beta phase appears. Okay. And the beta phase appears in the form of two spherical cup, two truncated spherical cup, and if I continue this particular cup, so this is one sphere, this is another sphere, but this part is not there and this part is not there. So, only this part is there. So, as if two truncated spherical cups are connected together and it forms a lens. Okay. Now, here if we see that the center part where this alpha beta interface was existing, that interface is out. Okay. So, now we have three interfaces. One is this gamma alpha alpha, this which is gamma alpha beta, and another one is this gamma alpha beta. So, now we can have this situation where I can make them as a vector quantity, and then these are the forces. I can also convert it in terms of surface tension, because surface energy can also be a surface tension. Okay. So, that time I have, this is the parting line, this is the theta, which is the contact angle. So, that time the situation is little different, because energy situation, energy equilibrium situation, alpha would be 2 gamma alpha beta cos theta. Okay. So, now again I can individually calculate the volume of this top part, volume of top part as well as the volume of bottom part. Volume of bottom part from the way we have done it for solid liquid interface when heterogeneous nucleation was taking place. So, now if I consider this one the volume would be, again it is a similar, it would be this particular volume would be so that means this volume and this volume would be similar, because two having the same radius, if this is the center, this is also R. So, both are having the same radius. So, the V1, if this is V1, this is V2, so V1 would be equal to V2, and that time the total V would be Now, if we try to find out the total surface area, again it would be total this is the total. So, that means that is S1 plus S2. Now, interestingly, if I try to do the same treatment the way we have done for heterogeneous nucleation, the expression would be so this delta G R with a negative sign, I mean to say that one interface is out. Whenever some heterogeneous nucleation is taking place, one interface is destroyed and or removed. That is what I have put delta G R, which is the removed interface, which contains the total surface area also. Now, if we do the same treatment the way we have done for heterogeneous nucleation in case of liquid solid, we would get delta G R heterogeneous would be equal to delta G R homogeneous S theta, and that time S prime theta would be equal to two. So, in that case, in the previous case where there were no such situation that two lenses are forming, there is only one lens was forming. So, that time in case of solid liquid case, S theta was two. There it was 4, because now that was considered in terms of one such cup, and here it is 2 such cup. So, that is why this 4 is replaced by 2, but the other things remain same. Now, interestingly, if we have some contact area, contact theta, there is existence of theta which is less than 90 degree. If I have that case, delta G R heterogeneous would be less than delta G R homogeneous, and from that we can also get R star would be similar like delta G S, as well as, since R these are, and so in this case if we consider these are, and in this case these are, both are same. So, that is what R star would not vary. The only thing that varies is prime theta. Okay. So, now you carry out this exercise, you would see that delta G star heterogeneous would be equal to delta G star homogeneous into S prime theta, and S prime is nothing but this. Okay. So, now at the same time we can also relate the heterogeneous nucleation rate, which will be again the similar. It will be again similar. So, now we can see that whether it is a solid solid transformation or it is a solid liquid transformation, we can get to the value of nucleation rate. Now, we have found nucleation rate for both the situation, okay, whether it is a solid liquid or solid solid, and at the same time whether it is a homogeneous or whether it is heterogeneous. Okay. So, that means once we know this, one term is known in our expression for overall kinetics, and if we try to see a very small quantity of phase which is forming, that means if we consider that the beta phase formation is pretty small. Okay. So, that time I can say that x equal to k t to the power n, I can convert it into power law, and we can also relate it to t to the power 4, and where I is the nucleation rate, which is this. Now, and this is in the case where I have a very small fraction forming in the parent phase. okay, and that is what we do not have any impingement effect between the phases. For example, let us say if this is the volume where phase transformation is taking place, if this is alpha, and let us say the beta is appearing like this, like this. So, that time the fraction of beta would be very, very small across the total volume, and then these beta will start growing but until unless it reaches to a sufficient size, these two grains will not interact between each other, and whenever this interaction comes, that time these two spheres would actually try to impinge each other. So, that impingement factor would come in the form of this exponential term, but if there is no impingement, then it would be power law. This entire thing will be taught by Professor Sangal. Okay. So, I am not getting into that, but at least you are clear that why we were interested in finding out I, because in order to find the overall crystallization, overall the transformation kinetics, and these particular expression would give me TTD diagram. Okay. So, that is what we wanted to do, all those treatments. Now, once we do this, we have to find out one more thing, which is U. Okay. U is equally important, because until unless we do not know U, we cannot get the information of transformation as a function of time at a particular temperature T. Okay. So, our discussion will be on U, how to find out growth rate, that means when this nuclei would start growing, that information we need to understand. And the second part, whatever we have considered till now, this is with reference to single component. We have to get to the multi-component, and we will go to the binary system first, and the next class will start with a binary system, and then we will see the how in case of binary this nucleation rate factor is tackled. Okay. Let us stop here, we will continue in our next lecture. Thank you.